Welcome to a tutoring session with Miss Taylor. Today we're going to be looking at ionic equations, and specifically balanced molecular, complete ionic, and net ionic equations with some product prediction. We're going to start with a double displacement example, and the text of our problem will say solutions of barium nitrate and cesium sulfate are mixed. So the first thing that you've got to do before you can predict products and do everything else is get the formulas for your two reactants. Now, the key word here, solutions, tells us that both of these are in the aqueous state. And the word aqueous, which you can also say aqueous, means that they are dissolved in water. And this is important because that means the separate ions are not joined together while in the water. And we'll talk about that more in a moment. But let's get the formulas. Barium, it's Ba, it's in group 2, so we know that it takes a positive 2 charge as an ion. Nitrate is a polyatomic ion, NO3, and it has a negative 1 charge. So the ratio of barium to nitrate is going to be 1 to 2. So the formula for that is Ba, NO3, keep the parentheses around it, 2. The cesium sulfate, cesium is a group 1 metal, so it would have a positive 1 charge as an ion. Sulfate is SO4, and it has a negative 2 charge as an ion. So that means it's going to take 2 sulfates for every, or 2 cesiums for every 1 sulfate, so that's CS2SO4. Okay, so now that we have those formulas, I'm going to start our balanced molecular equation. A balanced molecular equation is just the normal equation that at this point you should be used to writing. Shows our formulas, shows the states, and we balance it. Now, we have to predict the products for this. In a double displacement, it's pretty much the anions and cations are swapping places. So we are going to join the barium with the other anion, sulfate, and then we're going to join cesium with the other anion, nitrate. So our products are going to be barium sulfate, which, since they have the same charge, they combine in a 1-to-1 ratio. So BaSO4. And then these combine in a 1-to-1 ratio as well, CsNO3. And notice I haven't written in the states yet, because we have to consult the solubility rules. So barium sulfate, under soluble, sulfates are listed except barium. Things that are exceptions are the opposite. So an exception to soluble means it's insoluble. So we can go back here and say that this is a solid. All nitrates are soluble, also all group 1 metal compounds. So we've got 2 rules confirming that our cesium nitrate is going to be aqueous, because soluble means dissolved in water. Now, this is not a balanced molecular equation yet because we haven't actually balanced it, and it simply needs a 2 in front of the cesium nitrate, and everything else is balanced. That's usually not the terribly hard part. The complete ionic takes a little bit more time. Alright, so the complete ionic equation, all you do is take your balanced molecular equation, and your things that are aqueous need to be broken apart to reflect the fact that they are separate ions in water. You don't find cesium nitrate as a unit in water if it's aqueous. You find separate cesium and separate nitrate. So we're going to do this for all of the aqueous species. So barium nitrate is actually a barium ion and 2 nitrate ions. This is 2 cesium ions and a sulfate ion. I'm running out of space a little bit there, so I'm going to put my arrow here. Alright, our product. If it's not aqueous, you don't mess with it. So our solid just gets rewritten. And then our other aqueous product becomes 2 cesium ions in solution and 2 nitrate ions in solution. Now, the net ionic only involves the ions that actually go through a change, the things that react. So we can identify our spectators. Spectators only watch, so what ions we're only watching. So if we look, the nitrate is exactly the same on both sides of the arrow. The cesium is also exactly the same on both sides of the arrow. So those things are spectator ions, and they don't get to go to the net ionic equation. So our net ionic equation, we're just going to rewrite the things that we're not spectating. So the barium ion, the sulfate ion, and the solid that they form. Everything else was in the solution but didn't actually participate in the reaction. Next, we're going to look at a single displacement reaction. For our single displacement example, we're going to predict what happens when a piece of magnesium ribbon is added to a solution of copper 2 sulfate. Now, when you get magnesium in the lab, it's usually in the form of a ribbon, kind of looks like tape. So this is just elemental magnesium. So it's just magnesium. And then we have a solution, so remember that means aqueous, of copper 2 sulfate. Now that 2, remember, is the charge of your metal. So this is the charge of copper. So we actually have copper with a positive 2 charge, and it's bonded to sulfate, which we saw earlier. And since they are both 2s, they combine in a 1-to-1 ratio. Right, so now that we've got those, we can begin our balanced molecular equation. Now, magnesium is the elemental form, and in its elemental form, magnesium is a solid. And then we have our solution of copper 2 sulfate. And we have to predict the products of that reaction. Since this is a single displacement reaction, we have to consult the activity series. We're going to be comparing the magnesium to the copper in solution. So magnesium is there, and the copper is way down there. Since the magnesium is higher in the list than copper, it is more reactive and it will replace the copper in solution. So the copper is going to precipitate out, and then the magnesium is going to take its place. So copper lives in the solid state in its elemental form. And then since magnesium is in group 2, when it forms an ion, it takes the positive 2 charge. So the sulfate's already in solution, so they combine in a 1-to-1 ratio. But we need to check the state of magnesium sulfate. The question is it going to remain in solution or will it not? So now we have to go back to the solubility rules. And sulfates are listed under soluble. There's some exceptions, but magnesium is not listed as an exception. So magnesium sulfate is soluble, so it will be in the aqueous state. And this equation is actually balanced as written. There's 1 magnesium on each side, 1 copper on each side, and 1 sulfate on each side. now we can move to our complete ionic equation. And as I said before, as I was saying, we are only going to break apart the things that are in the aqueous state. So everything else just gets rewritten as it is up here. So I'm going to bring down my magnesium solid. The copper has a positive 2 charge as an ion, so I'm going to reflect that to show that it's a separate aqueous ion. And our sulfate ion. And go to the next line for our products. We've got our solid copper, and then our aqueous magnesium ion, and our aqueous sulfate ion. Notice that I did not add a charge to either the magnesium or the copper when I wrote the ionic equation. The only things that change are the things that are aqueous. If it's not aqueous, don't mess with it. And as long as you're looking at a single displacement or a double displacement reaction, you're not going to see a charge on a solid, liquid, or a gas. Really, the only things that can have charges are gaseous ions or aqueous ions. And you're not going to deal with a gaseous ion in a single displacement or a double displacement reaction. Alright, now we need to find our spectator ions in this, and there's only one spectator in this one. That would be the sulfate. So our net ionic equation just involves all of our metals. So our solid magnesium and our aqueous copper ion, they switch places and become solid copper and aqueous magnesium ion. And that is your net ionic equation. Thanks for watching.